So our next speaker is Professor Tejas Kalelkar from Indian Institute of Science, Education and Research. So his title today is Bounds on Pachner modes in cusped hyperbolic manifolds. So let's welcome.
Thank you.
Please.
Thanks. Yeah, so I'd like to be speaking about bounds on Pachner moves in cusped hyperbolic manifolds. This is joint work with my student Sriram. And to start with, I'd like to start with a very simple question. So is this a familiar knot? Now this knot looks fairly complicated, but if you kind of move things around, let me if I can, I don't know if there's a pointer over here, but if you move one strand, so you can move one of the strands. Yeah, okay. Wait, let me just see if there's a pointer over here somewhere. Okay. Anyway, so each of these moves, these diagrams represent small moves that you're making to the strands. And it's easy to see that you moved one strand to get to the next diagram, moved it slightly to get to the next one, and so on. And eventually you end up with the unknot. So this apparently complicated looking diagram is in fact just the unknot, the simplest possible knot. And what's nice about this diagram is that you actually need to make it more complicated in terms of the number of crossings before you can simplify it down to the unknot. So a basic question in knot theory, of course, is when are two knots equivalent? And what do I mean by equivalence? So we say two knots are equivalent if there is a homomorphism of S3, which takes one knot to the other one. And by a theorem of Gordon and Luke, this is equivalent to saying that the complements of the knots are homomorphic as topological manifolds. Now, the individual steps that you see over here of pushing these strands across, I'm sure most of you recognize them. They're just the Reidemeister moves. So Reidemeister moves are local small changes that you make to the diagram of a knot. And they are of three kinds. Either there is this kink, which you just snap out and make it tight, which is the Reidemeister move 1. Or you move one strand below or above the other strand. That's Reidemeister move 2. Or there's a crossing, and there is one strand kind of in between this crossing, which you move up across through this crossing. So that's Reidemeister move 3. And Reidemeister's theorem says that given any two diagrams of a knot, by a finite sequence of Reidemeister moves, you can move from one diagram to the other one. And there's a more recent theorem by Coward and Lackenby, who show that given two diagrams of a knot, D1 and D2, with M as the crossing number, then D2 may be obtained from D1 by a sequence of at most n Reidemeister moves, where this n, this bound n, is a fairly large number. It's 2 raised to 2 raised to 2. It's a tower of these exponentials raised to m, which is the crossing number. And the height of this tower itself is 10 raised to a million times m. So it is certainly not a practical bound, but as far as algorithms go, this does give us an algorithm for knot recognition. What you would do is you start out with D1 and then make a list of all the possible diagrams that you can get by at most n many Reidemeister moves. So you get a large but finite list of diagrams. And then you just compare each diagram with D2 just combinatorially. And if any of them are the same, then of course the two diagrams represent the same knot. But more importantly, if none of the diagrams in this list are combinatorially the same as D2, then D1 and D2 in fact represent different knots. So this gives a solution or an algorithm for the recognition problem. Now, by Gordon-Luke's theorem, knot recognition is equivalent to checking the homomorphism problem for the complement of the knot in S3, and S3 minus the knot being a 3 manifold does have a triangulation. So just as you have these local combinatorial changes that you make to a diagram, you have local changes that you make to a triangulation, and these are called Pachner moves. So given a triangulation of a 3 manifold, there are 4 possible Pachner moves, just as there were 3 possible Reidemeister moves. And the first one involves taking one tetrahedron and just splitting it into 4. Or you could take 4 tetrahedra which share a vertex, and then you combine them together to give one tetrahedron. Or you have 2 tetrahedra which share a face, and you split them into 3 tetrahedra. Or in the reverse direction, where you have 3 tetrahedra which share an edge, and you combine them together to give you 2 tetrahedra. So these are 4 possible Pachner moves in dimension 3. And Pachner's result, similar to Reidemeister's theorem, says that given any two triangulations of a 3 manifold, you can go from one to the other by a finite sequence of Pachner moves. And just as you have Alexander Coward's result for a bound to the number of Reidemeister moves, you have Mizhitovic's result, which gives a bound on the number of Pachner moves needed to go from one triangulation of a knot complement to another triangulation of a knot complement. And again, this leads to a solution to the homomorphism problem, an algorithm to solve the homomorphism problem, where you just start out with tau1, make a list of all triangulations you can get from tau1 by at most n many Pachner moves. It's a large but finite list. Compare each of those triangulations combinatorially with tau2. And if any of them are the same, then the two manifolds are homomorphic. If none of them are the same, then the two manifolds are not homomorphic. Okay, so this solves the homomorphism problem. But again, of course, the issue over here is that it's a fairly large bound, where even for n equal to 1, this would essentially be impractical with even modern day computers. Now, knots, for the most part, do have a little more structure than just the topology of the knot itself. Most knots happen to be hyperbolic. And of course, this is not a precise statement. So let me say some precise statements about what I mean by saying that a lot of knots are in fact hyperbolic. So if you look at knots with very small number of crossings, so Horst, Thistlethwaite, and Weeks have a really nice paper where they make a census of all the knots with at most 7 crossings. And this is a collection of more than 1,700,000 knots, of which all of them are hyperbolic except for 32 of them. Okay, so if you have small crossing numbers, then you can expect the knot to be hyperbolic. That's kind of just a general rule that I'm saying. And then, of course, if the theorem by Velasco says that if you have a prime alternating knot, which is not a 2Q torus knot, then it must be hyperbolic. And then a more recent result by Footer and Purcell say that if K is a knot which is not a 2Q torus knot, and if K has a prime twist reduced diagram where each twist region has at least 6 crossings, then the knot is hyperbolic. So in this diagram, you have 3 twist regions, and the first one has 1, 2, 3, 4 crossings, and the second region has 1 crossing, and the third one has 3 crossings. But the theorem says that if you have at least 6 crossings in each of these twist regions, then the knot ends up being hyperbolic. So the point I wanted to make is that there are a few theorems from which you can conclude from the diagram itself whether the knot is hyperbolic or not. Okay. Now, just as knots have complements in S3 which are triangulizable, hyperbolic knots have complements which are expected to be geometrically triangulizable. So a geometric ideal polyhedral decomposition of a manifold is a realization of the manifold as a quotient of a collection of hyperbolic ideal polyhedra by phase pairing isometries, such that the polyhedra glue together consistently to induce the complete hyperbolic metric of M. If all these polyhedra are in fact tetrahedra, then it's called a geometric ideal triangulation. So what's drawn over here is not a tetrahedron, it's just a pyramid. And now to see what this looks like geometrically, I put all these vertices A, B, C, D, and infinity on the sphere at infinity in H3. And then the different faces should now be totally geodesic planes in H3. So you have these vertical planes and you have the hemisphere at the bottom. This is what a typical geometric ideal polyhedron looks like. You combine these together by sticking them along their faces. And then if the induced metric on the manifold is the hyperbolic metric of the manifold, then you say that it's a geometric ideal polyhedral decomposition of the manifold. Now, the reason I bring this up is because of this result by Epstein and Penner, which says that there exists a canonical ideal polyhedral decomposition of any finite volume cusped hyperbolic 3-manifold. So one of the most popular and effective ways of recognizing knots practically speaking, hyperbolic knots practically speaking, is using software like Snappy. And the ways that Snappy works is that you start out with a topological triangulation of the knot diagram, and then it eventually runs an algorithm to come to the Epstein-Penner decomposition. It does this fairly quickly. Once you have the Epstein-Penner decomposition, which is just this canonical ideal polyhedral decomposition, because it is canonical, you can just compare the two polyhedral decompositions at a combinatorial level. And if the two polyhedra are the same, then the knots are the same. If they're not, then the two knots are not the same. Now, this is extremely effective, and it has been used for all kinds of census productions for knots and for cusped hyperbolic 3-manifolds. Of course, one glaring problem over here is that the algorithm isn't guaranteed to always give you the Epstein-Penner decomposition. If it does come up with the Epstein-Penner decomposition, then you know it is the correct one. But theoretically, there is no reason for it to always come up with the Epstein-Penner decomposition. In practice, it always does, but there is still no theory backing it up. So in particular, there isn't any runtime bound for such an algorithm because we don't know that it will always succeed for all cases. So this is the Epstein-Penner decomposition, which is the most successful or practical way of coming up with an algorithm. for recognition of hyperbolic knots. But as I said, the problem is that there is no runtime bound for it because it's not guaranteed to succeed as of now. And it is expected that all knots do have geometric ideal triangulations. The best result in this direction is by Hall and Purcell, which says that for every n more than equals 2, there exists some constant dependent only on n, such that if k is a link in a prime twist reduced diagram with n twist regions and at least cn crossings in each twist region, then the complement admits a geometric ideal triangulation. It's also proved that any hyperbolic knot has a finite cover which has a geometric ideal triangulation. So if you assume that you do know the geometric ideal triangulation, then what is the best you can do? So this is the question we asked ourselves. Is there an algorithm to check equivalence of hyperbolic knots when you are given geometric ideal triangulations of the knot complement? And this should be an algorithm which is easy to implement and has explicit practical runtime bounds. Because as I said, the algorithm by Snappy and all is not yet guaranteed to succeed. There are other algorithms. So for example, like the Alexander Coward result would give an algorithm, or the Mijitovics result would give an algorithm. But again, those are not, I would not call it practical runtime bounds, because you basically have this towers of exponentials of height 2 raised to something. So it's a pretty large number. So this is the question we asked ourselves, that if we restrict our attention not to all knots, but only to hyperbolic knots, and furthermore, you are given a geometric ideal triangulation of the knot complement. This is often the starting point for Snappy as well, because you start out with the topological triangulation, you solve Thurston's equations, and you hopefully end up with a geometric ideal triangulation. So given such a triangulation, the result that we have is the following. Let M be a complete oriented cusped hyperbolic three-dimensional manifold. Let tau1 and tau2 be geometric ideal triangulations of M with at most M1 and M2 many tetrahedra, and all the dihedral angles are at least theta naught. Let M equals M1 plus M2. Then the number of Pachner moves needed to relate tau1 and tau2 is bounded by this number n, which is a function of M and theta naught. And the number n is some constant times M raised to 11 by 2 divided by sine theta naught raised to 12n plus 27 by 2. So once you have a bound in the number of Pachner moves, as I argued before, you have an algorithm which checks the equivalence of the knot complements, and therefore the equivalence of the knots themselves. Along the way, we've also calculated a lower bound for the systole length of the manifold. So let M be a complete orientable cusp hyperbolic 3 manifold. Let tau be a geometric ideal triangulation of M with small m many tetrahedra and all dihedral angles at least theta naught. Then the systole length of M is bounded below by this constant time sine theta naught raised to 4n plus 7 by 2 divided by M raised to 3 by 2. So in the remaining maybe 10 minutes, I'll talk a little about what are the main ideas which are involved in the proof of the first theorem. How do we get this bound on the number of Pachner moves needed to go from one geometric ideal triangulation to the other one. So to start with, we have two geometric ideal triangulations, tau1 and tau2. And what we do is first we need a common geometric subdivision. So if I just overlap the two triangulations the way I've drawn over here, where you have these blue triangles and the red triangles, if you just overlap them together, then you do get a polyhedral subdivision. Okay, so you get a common polyhedral subdivision. And the first step in the proof is to get a bound on the number of polyhedra in this common polyhedral subdivision. Okay, so this is the first step in the proof. And the main ideas which go into this are the Margulis lemma, the thick-thin decomposition for cusped hyperbolic 3 manifolds. I'll come to this in a minute. And once you have a common subdivision, then its barycentric subdivision, this beta of tau1 intersection tau2, is going to give you a common subdivision for tau1 and tau2. And so instead of going from tau1 to tau2, we just go from tau1 to this common subdivision and from tau2 to this common subdivision. So the second part of the proof is to go from a triangulation to a subdivision of the triangulation by a bounded number of Pachner moves. And the combinatorial ideas which go over here is something called a Schelling sequence. And we use a result by Adifacito and Benedetti over here. So I'll come to both these parts of the theorem, both these parts of the proof. So the first one is to get a bound on this common subdivision. Now, just to say that this is not obvious, if you look at topological ideal triangulations and not the geometric ones, then this is not true that you'll have such a bound on the number of common polytopes in this common subdivision. So what I've drawn over here is a blue ideal triangle in H2. And then I've drawn an image of that on a cusp hyperbolic surface where all the vertices are at infinity, so they are in the cusp. And this is part, let's say this blue triangle is part of tau 1. And then we have a red triangle, which is part of tau 2, whose vertices are also at the same cusp. Now it's possible that the red triangle might wind around the blue triangle any number of times. So in particular over here, it's just winding around once, but it might wind around k times, right? And if I do that, then I've introduced k polyhedra in the common subdivision. So even with just two triangles, it's possible to have an unbounded number of polyhedra in the common subdivision if I just look at tau 1 intersection tau 2. Now, the reason this doesn't happen is because we're using geometry and we're using geometric ideal triangulations, not just topologically ideal triangulations. So Margulies' lemma is the following. It says that there exists a universal constant epsilon positive such that the set of M, which is the set of points with injectivity radius less than epsilon by 2, this consists of either tubes around closed geodesics gamma of length less than epsilon, or they are neighborhoods of the cusp homeomorphic to t cross 0, 1, where t is a flat torus. Okay, so the points where the injectivity radius is really small are either these tubes around small geodesics, or they are these torus cross I neighborhoods of the cusps. So this is Margulies' lemma. And then the way we use this to get a bound on the number of polytopes in the common subdivision, this is just an outline of the main steps involved. So using this thick-thin decomposition, we find a cusp torus T, which is deep enough in the cusp so that it only meets the vertical simplexes when I lift this to a triangulation of H2 or H3 over here. I've drawn it in H2, but of course what I mean is H3. So once I lift the torus to this photosphere, which is parallel to the XY plane in the upper half space model in H3, it should only meet the vertical simplexes. So I take this deep enough or high enough in H3. And therefore the triangulation induced on this flat plane is just a Euclidean triangulation. So you actually have your usual edges and so on the plane. And we can also ensure that the shortest closed geodesic in T is of unit length and the area of T is bounded in terms of the volume of the manifold. So we do have some kind of normalizations. And then as this tau bar is a Euclidean triangulation of a flat torus with bounded area and with triangles of angle greater than theta naught, because the dihedral angles of the tetrahedra I've assumed are at least theta naught. So when you intersect it with this flat plane sort of which is high enough, then you get a triangulation and the angles of these triangles are at least theta naught. So you've got a triangulation of a flat torus with bounded area and with triangles of angle greater than theta naught. So we can calculate a lower bound on the edge lengths of tau bar. Once you have a lower bound on the edge lengths of this triangulation, every vertex in this triangulation corresponds to an edge of the original triangulation, right? Because the edges are now vertical to this face. So all the vertices of this triangulation are in fact corresponding to these vertical edges. And so as vertices of tau bar are a certain minimum distance apart because we have bounded the lengths of these edges in tau bar. So we can find a lower distance bound among the edges of tau in the thick part. So what we've got is this triangulation tau. And if you look at the distance between the edges of tau in the thick part, then we've obtained a lower bound on the distance between them. So the edges are at least some small distance apart. Now what we do is we take one fixed tetrahedron delta and we intersect it with all the edges of tau 1. Now, because the edges of tau 1 are some minimum distance apart, if you look at the components of the edges of tau 1 intersection delta, and for each such component, you choose one point on this component and choose a small enough neighborhood so that you get balls which are all disjoint. Okay, because we've gotten some minimum distance between the edges of tau 1, so we can choose a small enough radius and obtain all these disjoint balls in this delta. Okay, so as all the polytopes, so what we've gotten is this distance between the edges of tau 1. Using that, we've gotten balls in delta, which are minimum distance apart. So they're all disjoint balls. And then using the fact that the volume of delta is bounded by the volume of any regular ideal tetrahedra, we get a bound on the number of edge components in E tau 1 intersection delta. So we've gotten a bound on the number of edge components in this E tau 1 intersection delta. And then we just say that all polytopes of this tau 1 intersection delta contain an edge which lies either in an edge of tau 1 or of delta. And for every edge, because the minimum angle is theta naught, so there are at most 2 pi by theta naught many polytopes which share a given edge. And so we get a bound on the number of polytopes in tau 1 intersection delta. Okay, and delta we can take as a tetrahedron of tau 2. And so we vary this delta over all the tetrahedra of tau 2. And this gives a bound on the number of polytopes in tau 1 intersection tau 2. Okay, so this is, of course, I know it's very quick, but it's just sort of the highlights of the proof, which goes into showing that you have a common subdivision of tau 1 and tau 2 with a bounded number of polytopes. Once you've gotten a common subdivision with a bounded number of polytopes, then the next step in the proof is to go from tau, a given triangulation, to some subdivision of tau. Okay, so we don't need to go from tau 1 to tau 2. We now just need to go from tau 1 to some tau star, which is a geometric subdivision of tau. And we know the number of simplexes in tau star. That's what we've just done. And of course, we know the number of simplexes in tau, which is given to us. So we have tau, we have a subdivision of tau, and we know the number of simplexes both in tau and in tau star. So it is enough to obtain a sequence of Pachner moves from this subdivision tau star to tau by changing the star of each simplex to a cone over its boundary. So a star of a simplex A is just the union of all simplexes which contain A. Okay, so how do I go from a subdivision to the original triangulation by a controlled number of Pachner moves? So this is what we do now. So to start with, let's take the red triangles are the original triangulation tau, and the black ones give me a subdivision tau star. So in order to go from tau star to tau, what I do is I start with tau star. I then take the star of the two simplexes. Now for a given two simplex, there is no other simplex which contains it. It's the highest dimension. So I start out with this red triangle, and then I just replace the red triangles by cones over their boundaries. So if you see what's happening over here, when I do this step, I have the boundary of the triangle, and then I'm just replacing the subdivision in the triangle with a cone over its boundary. I then take the edges. So I have the edge, and then I look at the union of all the simplexes which contain that edge. So this is what I get, the star of this edge. And then I replace the star of this edge with a cone over its boundary. Right? And when I do this, what you finally get is just the barycentric subdivision of the original triangulation. So in order to go from a subdivision to the original triangulation, what I need to do is look at stars of simplexes, and in a controlled number of Pachner moves, go from a star of a simplex to a cone over its boundary. So what I need to do in particular is start out with a convex polytope, which is triangulated, and replace it by a cone over its boundary in a controlled number of Pachner moves. This is the aim. Now, the property that I use over here is what's called shellability. So a shelling sequence is the following. So given a triangulation of a convex polytope, a shelling sequence delta naught to delta m is an enumeration of the tetrahedra of this triangulation such that delta j intersects the union up to delta j in two-dimensional disk subcomplexes. So what you see over here is a shelling sequence. You see 2 intersects 1 along a one-dimensional disk. So I'm having 3 intersects 1 union 2 in a one-dimensional disk. 5 intersects 1 union 2 union 3 union 4 in a one-dimensional disk. So whenever you have such a sequence, we call it a shelling sequence. Now, once you have a shelling sequence, it allows me to get a sequence of Pachner moves which give me a cone on the boundary. So I do this, a 1-3 move over here, a 2-2 move, 2-2, 2-2, and now there are 3 triangles which share a vertex. So I do a 3-1 move, and then I continue this process, and eventually I end up with a cone over the boundary. Now, if I have a shelling sequence, I can do this. Now, do I always have a shelling sequence in dimension 3? Unfortunately, this is not true because Rudin showed way back in the 50s that there are Euclidean triangulations of a 3 simplex which are not shellable. I think a big advance in this theory came by a recent result of Adipressito and Benedetti, who showed that if P is a triangulated 3 polytope, then its derived subdivision, its barycentric subdivision, is in fact shellable. So this is the result we use to get shellability. And so now if we have this subdivision tau star, then for each simplex A, the star becomes shellable. And so we can change it by Pachner moves to the cone over its boundary by as many moves as there are tetrahedra in the star. And we know how many tetrahedra are there by the first step. Performing this change for all simplexes inductively over the dimension changes tau star to tau by as many Pachner moves as there are 3 simplexes in tau star. Okay, so to wrap it up, to go from tau 1 to tau 2, I first get this common subdivision tau star, and I get a control on the number of simplexes in tau star. And then to go from tau 1 to tau star or from tau 2 to tau star, this common subdivision, I use this idea of Shellability and this result of adiprocity, which ensures that convex polytopes over here do become shellable. And therefore, I have a control on the number of Pachner moves needed to go from tau 1 to tau 2. Stop over here. Thank you.
So any questions? So if no question, let's thank our speaker again.